Hi everyone, welcome to gemchem. Now today's video is on atomic structure part 10 video, and here we will learn about calculation of exchange energy. And before starting, if you have not watched atomic structure previous videos, please do watch it. It will be helpful. I will give the link in the description box. Now let us start. Now what do we mean by exchange energy? Now see, when parallel set of electrons occupy degenerate set of orbitals, they can exchange their places, and this process of exchange gives rise to stabilization of the system, and this is measured in terms of exchange energy. That is, suppose for d orbitals there is 5 degenerate orbitals, right? And if one electron is placed here, it will be able to exchange places from here to here, or it can go to here. So this is how it exchanges places, and the amount of ways in which it can exchange its places can result in greater stabilization. So this is important. Now how we can calculate this exchange energy? This can be calculated using this formula. In factorial into k, k is a constant, proportionality constant here is told, and divided by n minus 2 factorial into 2 factorial. Now if we simplify this one, we get n minus 1 divided by 2, and here n is the number of degenerate electrons with parallel spins. Now we will calculate for each of the configurations for d orbitals. Now let us see. For d1. Now for d1, n equals to how much? For d1, n equals to 1. Now so E exchange will be equal to what? E exchange will be equal to 1 minus 1 k divided by 2, that is n minus 1 divided by 2, so it is 0. So there is no exchange energy. For d2, then n equals to 2, right? So E exchange will be equal to 2 into 2 minus 1 into k divided by 2, which will be equal to k only, because this one becomes 1 and 2 cancels. Now for D3 we will see. Now see, for D3 system, n will be equal to 3, right? So E exchange becomes 3 into 3 minus 1 into k divided by 2, and the answer comes to be 3k, because this one becomes 6 and this one is 3, 3 2s are 6 and 2 cancels. For next one, that is for D4, n equals to 4 unpaired electrons, so E exchange becomes equal to 4 minus 1 k by 2, and this is 4 into 3 by 2, so on cancelling we get 6k, right? Now we will see for D5. Now see, for D5 it is n equal to 5 unpaired electrons, so E exchange becomes as this, that is 5 minus 1 into k divided by 2 equals to 10k, right? And for D6 it is n equal to, see, for up spin there is how many electrons? 1 2 3 4 5, so for 5, and down spin there is 1, so we have to calculate differently for both cases. So E exchange in this case becomes as this, that is 5 into 5 minus 1 k divided by 2 plus 1 into 1 minus 1 k divided by 2, and it becomes 10k, right? So it is equivalent to which one? That is D5 plus D1, right? We can write it like this. Similarly for others, that is for this one it is D5 plus D1 we have seen. For this one we can write it as D5 plus D2. For D8 we can write it D5 plus D3, D9 D5 plus D4, because we are dividing up spins with as D5 and down spins with their relative spins as D1, D2, D3 and D4. So these are the down spins which are being considered. So this one will be, see, D5 is always 10k plus D2 equals to k, so it will be 11k, right? Now for D8 D8 it will be equal to 10K plus 3K for D3. So it will be equal to 13K. Now for D9, what will be the exchange energy? Let us see. For D9, it will be 10K plus the energy for the other one, that is D4. So 10K plus 6K gives 16K, and for D5 it is 10K plus 10K, which is equals to 20K. So we can see that exchange energy is highest for D10. So that's why this is the most stable configuration we have obtained. Now hope this was helpful. This was a short video and thank you for watching. Do not forget to like, share, subscribe and comment.